Hello everyone, welcome. Today I'm looking at geometry problems. Now in geometry proofs, we actually use theorems, geometry theorems to prove certain concepts and certain facts with regards to geometry. So in our example number 1 today, we are told that we have two circles here that intersect at F and E. So we have circle ABFE and circle DCFE, which intersect at F and E. And we're also given that AED and BFC are straight lines over here. The required information is to prove that AB is parallel to DC. Prove that AB is parallel to DC. Now, which circle theorem are we going to apply here? And the answer is, if I would remind you that we have a theorem that says if we have a cyclic quadrilateral, a quadrilateral whose vertices lie on the circumference of a circle, if one side of a cyclic quadrilateral is produced, that means extended and maintained as a straight line, the exterior angle so formed, that angle there, must be called the interior opposite angle. This is the theorem we're going to apply here. However, if you notice here, the common chord FE is not drawn. So we have to draw that common chord FE. We must draw that common chord FE as follows. There is a diagram with a common chord FE drawn. And I've labeled the angles at E as E1 and E2. So the target, remember, is to prove that AB is parallel to DC. Now, if you look at cyclic quad ABFE, you'll realize that AE is produced to D. Therefore, E2 is an exterior angle so formed. It must be equal to the interior opposite, angle B. If you look at cyclic quad DCFE, you'll see that DE is produced to A, and therefore E1 should actually be equal to angle C, because that's an exterior angle. It must be equal to interior opposite angle. Now, let's go into it then. The question says we must prove that AB is parallel to DC. So we have to mention that construction there, because normally it will carry 1 mark. So construction. And in construction, we have to state what we're doing. So we're saying draw common chord FE. Most of the time, that code will be drawn for you, which means you would not need construction. Now, let's go straight to proof after stating our construction. So, we're going to say, with notation in the figure, I like to say that you don't have to, but I like to say that with the information shown in the diagram, what do we know? We know that angle B is actually equal to angle E2. And this is exterior angle of cyclic quad. Let's mention the cyclic quad BFEA or ABFE. ABFE. We can say also what? Also angle C up there is equal to angle E1, because angle E1. Exterior angle of cyclic quad. The cyclic quad we're interested in now is DCFE. DCFE. Now we have two equations here, which we can add by addition. What do we mean when we say by addition? We're basically saying, let's add the two equations. Angle B equals angle E2. Angle C equals angle E1. Let me add these equations up like so. So what do I have now? I have angle B plus angle C is equal to angle E1 plus angle E2, like so. So angle B plus angle C equals angle E1 plus angle E2. But notice now, they have told us that AED and BFC are straight lines. That means we can say, but E1 plus E2, these must add up to 180 because they are adjacent angles on a straight line. Now, if E1 plus E2 is equal to 180, therefore, surely angle B plus angle C should also be equal to 180. Therefore, angle B plus angle C should also be equal to 180 degrees. Now, there's something important about this, that if these angles add up to 180, what can we say about these lines? Let me take you back to the lower grades. In the lower grades, you were told that if two parallel lines are cut by a transversal, two parallel lines are cut by a transversal, this line is parallel to this line, you were told that co-interior or allied angles are supplementary. In other words, these two angles must add up to 180. Let's talk about the opposite of this. If I'm told that two lines are cut by a transversal, nothing is mentioned about the lines, whether they are parallel or not. If I'm told that these angles are supplementary, for example, let's say this angle is 120 and this angle is 60. If I'm given that, it follows, so that's a transversal as well, it follows that these lines must be parallel. If the lines are parallel, allied or co-interior angles must be supplementary. If allied or co-interior angles are supplementary, the lines must be parallel, converse, so to speak. So we're going to say here now, therefore, we're going to say, therefore, AB must then be parallel to DC. Why are these lines parallel? Because co-interior angles are supplementary. Okay, this should mark the end of question 1. That's how you'd set out the proof for question 1, where we were given, let me just remind you, we were given that we have two circles, ABFE and DCFE, which intersect at F and E, and we were told that AED and BFC are straight lines. They required us to prove that AB is parallel to DC, and this is how you set out the proof. Please take note that this is a past exam question, so please have a good look at this and make sure you understand what's going on here. Right, now I'm moving on to question number 2, still proving involving circle theorems. This question number 2 there. Now we are given circles AC and BC, which touch externally at C. The question requires us to prove that angle ACB is equal to 90 degrees, like this. We are also told that AB is a common tangent in the given information. So given circles AC and BC touch externally at C, and AB is a common tangent, we are required to prove that angle ACB is equal to 90 degrees. Now, normally, when two circles touch externally, the first thing that you would need to try and check is, if I draw a common tangent there, would it lead me to a solution? Unfortunately, in this case, that's the only plausible approach you would take. There's no way you can draw another tangent here, because this tangent would be very far away from that tangent and that other piece of information given. So we set out the proof to this question by constructing a common tangent there as follows. There is a common tangent constructed, and I've labeled the angles there as A1, A2, and A2 I've labeled it as small letter a. I'm going to explain why it has to be equal to this angle here, which I've labeled C2. So we have C1, C2, and this would be C3, if we are to name around the circle, that would be C3 and that would be C4. So C1, 2, 3 around the point. If we are to name these angles around this point C, we're going to say C1, C2, C3, C4. Now, at this point here, we have angle B1 and B2. And I've labeled these as small letter b, those ones, B2 and C3. I will explain shortly. Now, construction requires us to put a common tangent here, PCMQ. I've marked this point M because it's important for us to notice that this point M here would be regarded as an external point to all the tangents. This is an external point to tangent MB and MC. It's an external point to tangent MA and MC. Now, there's another theorem that we are supposed to apply here, having drawn that, having made that construction of a common tangent. The theorem says, if I am told that two tangents are drawn from the same external point to a circle, these two tangents must be equal in length. And therefore, we can comfortably say that MB is equal to MC is equal to MA. They are equal in length because they are tangents from the same external point to a circle, if you consider each circle. Now, we set out a proof to the fact that angle ACB is 90. Remember, the question says, prove that angle ACB is 90 degrees over here. So, we're going to say construction. We're going to say draw common tangent PCMQ as shown in the diagram. And then we go to proof now. So let's look at triangle AMC. In triangle AMC, what do we know about that? What we know is that AM is equal to MC. Why are those equal? Because they are tangents from an external point and one or same external point. Therefore, we can say, check this out, A2 must be equal to C2. A2, that angle must be equal to C2. Why? Because they're angles opposite equal sides. You must have covered this theorem in the lower grades as well. And we are calling this small letter A. Let's go to the other triangle. So here is triangle AMC. Now we are considering triangle BMC. In triangle BMC, what do we know? We know that BM is equal to MC. Like we said here for the other triangle, the reason is again tangents from an external point or from the same external point are equal in length. So we can say also, therefore, angle B2 is equal to angle C3. Angle B2 is equal to angle C3. Why is angle B2, this angle here, equal to that angle, C3? Because they are angles opposite equal sides. So, angles opposite equal sides. And we call this one small letter b. Now, I want to talk about the entire triangle ACB and add up all the angles in there. Let's see what we get. If we add up all the angles in there, we're going to get something very nice. If we add up all the angles, we're going to get the following. If I add up all the angles in the triangle here, I'm saying if I add up all the angles, angle A2 plus C2 plus C3 plus B2, it must give me 180 because I'm talking about the sum of angles in a triangle. So now we're saying in triangle ABC, comma, in triangle ABC, we're adding up all those angles, and we're saying that we have A2 plus C2 plus C3 plus B2. This must be equal to 180, and we're saying sum of angles in a triangle. Sum of angles in a triangle. Now, what is A2? Well, A2 is A plus. What is C2? Well, A2 is small letter a, C2 is also small letter a. You can see it here. Small letter a, and then small letter b, small letter b. So we are saying small letter a over here plus small letter a plus small letter b plus small letter b again equals 180. Now, if you do the addition there of like terms, this gives you 2a plus 2b is equal to 180. Let's factorize left hand side. 2 open brackets, a plus b equals 180. And if we divide by 2 both sides, 2a plus b all over 2 equals 180 all over 2. These cancel. So a plus b is equal to 90 degrees. Let's go back in the diagram and see which angle is this a plus b equal to. If you go back in the diagram, you'll see that angle a plus b, here we're saying we want to see which angle a plus b is equal to, because we've done the simple algebra manipulation of the equation. We found that a plus b equals 90. So I'm saying to you, which angle is a plus b? If you look at the diagram here, angle a plus b is actually this angle here, that angle there, which is the angle they're asking us to prove that is equal to 90, ACB. So we can comfortably conclude that therefore we know that this is angle ACB. This is equal to 90 degrees, and that's the end of the proof for number 2. Now I'm moving on to question number 3, still proving involving circle theorems. Here is number 3. Question number 3, we are told that we have two circles AXD and BXC, which touch externally at X. And we have common tangents AB drawn and DC drawn. So the common tangents AB and DC are drawn in the given formation here. It says given circles AXD and BCX, which touch externally at X. We are told AB and DC are tangents to the circle. So AB is the tangent to circle AXD and also to circle DXC. We are also told that DC is a tangent to the bigger circle DXA, and the same DC is also a tangent to BXC. We are required to prove that DC is equal to AB. Now, I spoke about tangent circles that touch externally, that the common tangent would be the best point to start from. In this case, if you draw the common tangent there, it's very difficult to connect the triangle formed that side and this side, or triangles formed there and here. So in this case, drawing a common tangent does not provide an easy solution for us. So therefore, we would perhaps try and draw, produce AB to some point and produce DC to some point, so that these two tangents meet somewhere at the external point, as follows. There you have it. Now there is construction there. I'm saying produce AB to produce AB and DC to meet at T. Now you notice there's something very beautiful here, that ABT and DCT, those are tangents from the same external point to the bigger circle. And if you look at BT and CT are tangents from the same external point to the smaller circle. So there I have somewhere to start from. So I'm going to say construction. And I'm saying produce AB and DC to meet at T. That's my construction. Then I can go straight into proof now. What am I saying? I'm saying in proof, I don't have to say with notation. In the figure, I can just move straight and say the central point has been given as X there. Don't forget, point of contact has been given as X. So I can say in circle AXD, comma, I can say AT is equal to DT. The reason for that is tangents from an, that's one, external or same external point must be equal in length. And I'm gonna also say, so let me call this equation number one. And then I'm coming to the smaller circle now. I'm gonna say in circle BXC, comma, I can say BT is actually equal to DT. Same reason, tangents from an external point are equal in length. I'm going to call this equation number 2. Now, these two equations, I can put them together. I'm going to need paper here. I can put them together, these two equations, as follows. If I put the two equations together, I'm going to obtain something like this. I'm going to subtract, because AT and DT are equal. BT and DT are equal. So AT and DT, AT and DT, and then here I'm saying BT equals CT, not DT, equals CT. Please take note of that. Sorry for that. Sorry about that. So I'm saying basically that AT is equal to DT for the bigger one. And for the smaller circle, I'm saying BT is equal to CT. BT equals CT. Right. So if you allow me to make sure that this is clearly seen here, then what I'm saying now is, if I take equation number one, and I subtract equation number 2. If you remember in example number 1, I told you we can add or subtract equations. So in this case, if I say number 1 minus number 2, I'm basically saying AT, which is equal to DT, and then I'm saying here BT, AT equals DT, BT equals CT. When I subtract the 2, I'm going to get AT minus BT is equal to, this one minus that must give me DT minus CT. Now, so subtraction of equations works, addition of equations also works. Let's go back to the diagram and check what this is. What is AT minus BT equal to? If you come back here, and if you check, AT minus BT is actually AB. Because if this was 15 and that was 12, I would say to find this distance here, it would be 15 minus 12, it would give me 3 there. Same story, if this was 15 and that was 12, I would say 12 from 15, it gives me 3 there. So this equation actually makes sense. So we can comfortably say that AT minus BT is equal to AB. That is actually AB is equal to, coming back here, DT minus CT. DT minus CT is actually DC. This is actually DC. If you check, this is what the question required us to prove here. Prove that AB equals DC. Prove that AB equals DC. So by extending these so that they meet somewhere here, external point, common external point, we have been able to prove that it is true that AB is equal to DC there in our proof here. So we can say this is where question number 3 ends. I'm moving on to number 4, the last one for today. We're still doing proofs. Question number 4, the last one. I said question number 1 was a past exam question, and question number 4 is also a past exam question. Now we have been given here that we have circle ABC, and in which CT is a tangent, and we're told ABT is a secant. And we know what a secant is. A tangent produced to an external point forms a secant, and then we have a tangent there at C. They now are saying that we must prove that CT squared is equal to AT times BT. Now, whenever you see squares like this, there's similarity involved. So what I'm going to do now is to look at the triangles. We have 3 triangles here. We have triangle ABC, we have triangle BCT, and we have triangle ACT. But our triangles of focus are going to be the bigger one, ACT, and the smaller one, BCT. Why are we separating the triangles in that fashion? Is because we see angle T is a common angle found in both triangle BCT and ACT. We also notice that angle C here, if I call this angle C2 or C1, you'll see in the diagram shortly, it is equal to that angle because of Turncott theorem. Yet another theorem that you need to remember from circle geometry. It says if I am given a circle and a tangent to the circle, like so, or like this, and there's a chord drawn at the point of contact, the angle between the tangent and the chord is equal to the angle that the chord subtends at the circumference in the ordinate segment. The angle between the tangent and the chord is equal to the angle that the chord subtends at the circumference in the ordinate segment. So that is called Turncott theorem. This is the theorem we're applying here. Now, let us see how we separate the 2 triangles. There is the diagram I've drawn with markings of the angles as shown, but I said we need to separate the triangles. So I'm going to separate the triangles as follows. That would be my bigger triangle. I'm going to call it ACT. And then I'm going to check this one here, which I'm going to call ABT. BCT. So this is BCT. Remember, this is C1. And remember, this is B1. This is C1, which is equal to that. And the angle T is a common angle. So there is a common angle. And there's your angle C1, which is equal to angle A. Now, you can see that we have 2 angles equal in the 2 triangles. So that angle there is equal to that angle, Turncott theorem, the common angle, and therefore that angle there must be equal to that angle there, known as third angle of a triangle or angle sum of a triangle. Therefore, it means that these 2 triangles are similar because they are equiangular. Triangles that are equiangular are similar. So let's set out the proof as follows. So we are going now to say, no need for construction here. We're going straight to proof. And then we mention the triangles, these 2. In triangles ACT, and now watch how I'm naming these triangles. I'm following equal angles, ACT. In this triangle, I must say C, because these angles are equal. So I moved from A and I went to C. Here I must move from C, I must go to B, because these two angles are equal. And then I must end up at C, which are also common angles, or common angle. So now I'm going to say a triangle ACT and triangle CBT. CBT, comma. We can say this triangle here, angle A, is equal to angle C1. Tan chord theorem. And we can say angle T is common. Some people like to say angle T is equal to angle T, whichever works for you. And then we can also say, therefore, angle ACT is equal to angle CBT, the angle of a triangle, like so. Now, 3 points, 1, 2, 3 points. That should be sufficient for us to conclude that the triangles are similar. So we're coming up with the conclusion. And the conclusion says, here, we are saying, therefore, triangle, the way we named them, ACT is similar to triangle CBT. Why are these triangles similar? Because they are equiangular. You write angle like that. From here we can say, hence, we draw proportionality. From there, AC, first 2 divided by first 2 all over CB is equal to last 2 over last 2, CT all over BT. And then we're moving on, first last over first last. So I'm going to say AT all over CT. Why is this the case? Because the triangles are similar. Triangle ACT is similar to triangle CBT. That's the reason why we have that ratio to be true. Remember, equiangular triangles are similar. We also have a theorem that says if the triangles are such that their corresponding sides are in the same proportion, the triangles are equiangular and similar. So in this case, we have those triangles to be similar. We can draw proportionality like this in terms of other ratios. Now we see the common side CT here. It means we're going to be interested in that part there. I'm going to rewrite that to CT over BT is equal to AT over CT. And if you cross multiply, you are going to obtain CT squared is equal to AT times BT. And if you check, this is exactly what the question required us to prove over here. Question said, prove that CT squared equals AT times BT. CT squared is equal to AT times BT, which is exactly what they wanted us to prove. So this would be the end of our proof for question number 4. Right, I am going to stop here as far as proofs are concerned. I will come back with another video that involves now calculation of angles and perhaps a little bit more similarity and questions around proportionality. If you're new to this channel, please subscribe and share these videos. Give them a thumbs up. It will go a long way in growing this channel, so we can continue giving him more content, and we're hoping that this content is making a difference somehow. All right, see you next time.